Okay, so the first part of this question is just three definitions about three different terms that we use relating to waves. So the first one, wavelength. The important bit with this one is to make sure you're talking about two identical points on a wave, but it has to be the two waves next to each other. Right, so you might write something like the distance between two adjacent identical points on adjacent waves. Then for frequency, that's how many complete oscillations a wave makes in 1 second or per unit time. And then a period is just the total time taken to do one complete oscillation. Okay, so this next question takes the terms that we just defined, and then it's asking us to give the logic behind the equation that relates these three, lambda, f, and v. So it says to start from v, so we have, in 1 second, we have f wavelengths produced, because f is the frequency, the number of times it oscillates per second, and then the distance travelled by the first one that's produced in 1 second is going to be f times lambda, because lambda is the actual length of the wave, and f is the number of wavelengths produced, so you then get f lambda equals v. Okay, so for this question, we're looking at a tube where we've got one end submerged in water and then we've got one open end. So if we've got a loudspeaker pointing down at this tube, and we're given that it's at 512 Hertz, this is the wave pattern that we get formed from a standing wave pattern. So the important things to take from this are that at a closed end of a tube, you have to have a node, and at an open end, you have to have an antinode. So the question then says, it gives us this tube, which is much longer, same setup with a loudspeaker. So where this bit is the same as our original tube, but now it's much longer, it says sketch the standing wave pattern in this tube. So I've sketched it here, as you can see. The important things that you have to get right in this one are, you have to have this node at the closed end, and then another node where you've got this half a wavelength distance, and then an antinode at the top. It's just as the same as this tube. Open-ended tube has to be an antinode at the top. You can't possibly have this guy going all the way to the top, because you have to have these boundary conditions where it's an antinode at the open end. So the second part of this question is, it says label with an A or an N where the nodes and antinodes are. So we've got a node at the bottom because it's closed, we've got an antinode here, another node, and a final antinode. Okay, so this next part of this question is, it says calculate the speed v, the speed of sound in the tube. So we know we've got this distance here, and we know that this is half a wavelength, this distance here. So we can say lambda over 2 is 0.33 meters. It's important to do it in meters. We've just had our equation for v equals f lambda, so we can do v equals f lambda, like that. So we have f times 2 times lambda over 2, which is this guy, is f times our lambda, and we have our frequency we're given is 512 Hertz, times this 0.66, 2 times this guy, and we get out, nice and easy, 338 meters per second. Okay, so we've now got a new setup. So we've taken the tube completely out of the water, so we've got both ends are open. The tube is 66 centimeters long, and we're sticking with the same frequency of 512 Hertz. So it says that we get a loud sound out of this setup, so we know that we've got a matched up waveform. So it's going to have an antinode at this end and an antinode at this end, because we've got both ends are now open. So it says sketch the stationary wave now produced in the tube, so we can do that nice and easily. Very similar to the last one, antinode at the top, another antinode in the middle, and an antinode at the bottom. Okay, so you can do this, if it makes it easier to draw, you can just divide the tube up into 4 bits, like that. Okay, so then for the next setup, it says state the fundamental frequency, f0, of the stationary wave in the open tube. Okay, so this is not the fundamental frequency. Here we've got multiple patterns that look the same in different parts of the tube. So the fundamental frequency is going to be half of this. So if we turn the frequency down, when the fundamental frequency is set up right, we're going to have a quarter of a wavelength in the tube. So we're going to have an antinode at both ends still, but we're just going to have one pattern like this. So we're going to start with an antinode at the top, a node in the middle, antinode at the bottom end. Just finish the drawing like that. So with this, the wavelength is twice as long, which means the frequency is half. So for this guy, for our fundamental frequency f0, we have 256 Hz rather than 512. Okay, so the last part of this question says, explain why the stationary wave in this part is the second harmonic for an open pipe. So just like I was just saying, so this is our fundamental frequency, this is our second harmonic. The reason why this is only our second harmonic is that, like I said, we've got to have an antinode at both ends of this tube because it's got open ends. So as we turn the frequency up, this is our fundamental, and we can't have the situation where we get 3/4 of a wavelength along the tube, because that's going to put a node at the top end of this, which is not allowed because it's got an open end. And so the next configuration up, where you've got a system that works and you have an antinode at both ends, is when you have twice the frequency, which makes this guy the second harmonic.